Picture this: a vast, shimmering tapestry of light stretching across the cosmos, a relic from the earliest moments of our universe. This is the cosmic microwave background, the faint afterglow of the Big Bang itself. But hidden within this ancient glow lies something strange, a mysterious cold spot, a void where the temperature dips unexpectedly, defying everything we think we know about the universe. What if I told you this anomaly might not just be a cosmic accident, but evidence of something far more extraordinary? What if it's a fingerprint, a scar left behind by a collision with another universe, a parallel reality brushing against our own? The idea sounds like science fiction, but scientists are seriously considering it. Imagine for a moment that our universe isn't alone, that beyond the edges of everything we can see, there are other realities, other versions of existence, each with its own laws, its own history. And sometimes, just sometimes, those worlds might bump into ours. The cold spot in the cosmic microwave background could be the echo of such a collision, a cosmic bruise marking where two universes briefly touched. It's a theory that challenges everything we thought we knew, blurring the line between physics and philosophy, between what's real and what's possible. This isn't just about solving a scientific puzzle, it's about rewriting the story of existence itself. If this cold spot really is evidence of a parallel universe, it would be one of the most profound discoveries in human history. It would mean we're not alone in the grandest sense imaginable, and that's what makes this journey so thrilling. Over the course of this video, we'll dive deep into the science behind this mystery, exploring the mind-bending theories, the cutting-edge research, and the tantalizing clues that could unlock secrets beyond our wildest dreams. So buckle up, because we're about to venture into the unknown, where the rules of reality might not be what they seem. To understand why this cold spot is so puzzling, we need to rewind the cosmic clock nearly 14 billion years, back to the birth of the universe itself. Picture the Big Bang not as an explosion in empty space, but as the moment space and time burst into existence, flooding the newborn cosmos with unimaginable heat and energy. Over hundreds of thousands of years, that searing plasma gradually cooled, allowing atoms to form and light to finally travel freely. And that light, stretched by the expansion of the universe into faint microwaves, is what we now call the cosmic microwave background. It's like a snapshot of the universe in its infancy, revealing a remarkably uniform glow almost everywhere we look. But here's where things get strange. While the CMB is incredibly consistent, with temperatures varying by less than 100,000th of a degree, there's one region that stands out like a cosmic sore thumb. The cold spot, first detected in 2003, spans an area of the sky about 5 times wider than the full moon. It's not just slightly cooler, it defies our best models of how matter and energy should have distributed themselves after the Big Bang. Statistically, such an anomaly should be nearly impossible in our current understanding of cosmology. Think of it like finding a single, perfectly frozen patch in an otherwise steaming cup of coffee. It shouldn't be there, and yet it is. Scientists have proposed all sorts of explanations, from measurement errors to exotic physics. But one theory is bolder than the rest. What if this cold spot is a bruise left behind when our universe collided with another reality entirely? Imagine 2 soap bubbles floating in a higher dimensional space, briefly touching before drifting apart. Where they made contact, there'd be a distortion, a scar. That's the kind of scenario some physicists are seriously considering. It's not just wild speculation. Supercomputer simulations show that a collision with a parallel universe could, in theory, leave behind a telltale cold imprint in the CMB. Of course, extraordinary claims need extraordinary evidence, and that's where the real detective work begins. Teams of astronomers are scrutinizing this anomaly with ever more precise instruments, searching for clues hidden in the patterns of galaxies, the warping of space-time, and even the ghostly whispers of gravitational waves. The cold spot might be a fluke, a cosmic illusion, but if it's not, it could be our first glimpse into a multiverse, proof that we're just one universe among countless others. And that changes everything. The discovery of this cosmic anomaly didn't happen overnight. It unfolded as astronomers pieced together data from some of humanity's most advanced telescopes. The story begins with NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, which spent nearly a decade scanning the sky in the early 2000s. WMAP mission was to create the most detailed map yet of the cosmic microwave background, measuring temperature variations down to fractions of a degree. At first glance, the data matched expectations, a nearly uniform sea of microwaves with tiny fluctuations. But then, researchers noticed something odd, a region in the constellation Eridanus where the temperature dropped just a bit more than anything else in the map. It wasn't a mistake. The same cold spot reappeared when the European Space Agency's Planck satellite, armed with even more sensitive instruments, scanned the sky years later. We're not talking about a small blip on the cosmic radar. This cold spot spans roughly 1.8 billion light-years, an unfathomable stretch of space so vast it would take light, the fastest thing in the universe, nearly 2 billion years to cross it. To put that in perspective, if you held a grain of sand at arm's length, the cold spot would cover an area about 10 times larger than that tiny speck in the sky. And the temperature, it's not just slightly cooler. It's about 70 microkelvin colder than its surroundings, a deviation that shouldn't exist according to standard cosmological models. For context, that's like finding a single ice cube chilling in a bathtub of perfectly warm water, defying all logic. What made this discovery even more baffling was the absence of any obvious cosmic structure to explain it. Normally, cold spots in the CMB can be tied to vast voids, regions of space with fewer galaxies and less matter. But when astronomers mapped the distribution of galaxies near the cold spot, they found nothing unusual. No giant void, no hidden cluster of matter warping light, just ordinary space behaving in anything but an ordinary way. It was as if the universe had left behind a cryptic clue, a puzzle with missing pieces. Some researchers argued it could be a statistical fluke, a random blip in the data, but the odds of such an anomaly appearing by chance, less than 1 in 50. The cold spot wasn't just an outlier, it was a cosmic mystery demanding an explanation. This is where the real detective work began. Teams of scientists combed through the data, testing one hypothesis after another. Could it be an instrumental error? Unlikely. Both WMAP and Planck, completely independent missions, had seen it. Was it the shadow of some unseen structure bending light on its way to us? Observations ruled that out too. The only remaining explanations were the ones that pushed the boundaries of physics itself. Among them, the possibility we were seeing the aftermath of a collision with another universe, a ripple in the fabric of reality left by something beyond our own cosmic horizon. The implications were staggering. If true, this cold spot wouldn't just be a curiosity. It would be the first physical evidence of a multiverse, a smoking gun that our universe is just one bubble in an endless cosmic foam. That's why astronomers continue to study it with cutting-edge tools, from next-generation space telescopes to galaxy surveys mapping the large-scale structure of the universe. Because if this anomaly holds the key to understanding parallel realities, it's not just a scientific breakthrough, it's a revolution in how we see existence itself. When astronomers first stumbled upon the cold spot, their immediate instinct was to search for a cosmic structure that could explain it, the leading candidate. A supervoid, an enormous, nearly empty region of space where matter is so sparse that light passing through it loses energy, creating a slight cooling effect in the CMB. It's like walking into a shadow cast by a cosmic skyscraper. If such a void existed on the scale of the cold spot, it would easily be the largest structure ever observed, dwarfing even the Sloan Great Wall, a filament of galaxies stretching over 1.4 billion light-years. But here's the problem: voids that big shouldn't exist. According to our best models of cosmic evolution, matter should be distributed relatively evenly across the universe, with only small, localized voids forming between galaxy clusters. Finding one large enough to explain the cold spot would be like discovering a city-sized sinkhole in the middle of an otherwise flat desert. It defies the natural processes we understand. Even more puzzling, when astronomers trained their telescopes on the cold spot's location, they found no sign of a corresponding void. Galaxies were spread in that region just as densely as anywhere else in the universe. It was as if someone had erased the skyscraper but left the shadow behind. This discrepancy forced scientists to reconsider. Maybe the void wasn't completely empty, but just had slightly less matter than average, an underdense region rather than a true void. Yet even that explanation fell short. Detailed calculations showed that even the most extreme underdensity possible under known physics couldn't account for the temperature drop observed in the cold spot. The numbers simply didn't add up, and without a visible cosmic structure to point to, the supervoid hypothesis started to look more like a cosmic dead end. That left researchers with an even stranger possibility. What if the cold spot wasn't caused by anything inside our universe at all? What if it was a fingerprint of something beyond, a defect in the very fabric of spacetime itself? Some theorists began exploring the idea of a cosmic texture, a rare and exotic type of topological defect left over from the early universe. Think of it like a wrinkle in the universe's structure, a place where the rules of space and time twist slightly out of alignment. These textures, if they exist, could create exactly the kind of temperature anomalies we see in the cold spot. But textures are speculative. No one has ever detected one, and their existence relies on untested physics from the universe's first moments. Which brings us back to the most tantalizing explanation of all: a collision with another universe. If our cosmos is just one bubble in a vast multiverse, then the cold spot might be the mark left by a neighboring bubble brushing against ours in the seething quantum foam of higher dimensional space. It's a mind-bending idea, but it's one that's proving harder and harder to dismiss. After all, when every conventional explanation falls short, sometimes the most extraordinary answer is the one that fits. The supervoid theory seemed like the perfect answer, an elegant cosmic shadow to explain the cold spot's chilling presence. But as scientists dug deeper, cracks began to show. Recent galaxy surveys, using some of the most powerful telescopes on Earth, have delivered a knockout punch to this once promising explanation. When researchers mapped the distribution of matter in the cold spot's vicinity, they expected to find a gaping void, a cosmic emptiness stretching across billions of light years. Instead, they found something startlingly ordinary. The galaxy counts just didn't add up. There was no void, no vast desert of missing matter. In fact, the region looked almost indistinguishable from any other patch of the universe. This wasn't just a minor discrepancy. To create a temperature drop as extreme as the cold spots, a supervoid would need to be so massive and so empty that it would rewrite our understanding of cosmic structure formation. Statistically, the odds of such a void existing where we see the cold spot are staggeringly low, less than 2%, according to some analyses. That's like rolling a die 100 times and never once landing on a 6. Possible, technically, likely, not even close. Even more damning, computer simulations of the universe's evolution show that voids large enough to explain the cold spot simply shouldn't exist in our current cosmological model. The universe's matter is spread too evenly, its web of galaxies too interconnected to allow for such an enormous empty bubble to form naturally. It'd be like finding a single, perfectly circular hole punched through a spider's web. Nature doesn't work that way. So if it's not a supervoid, what's left? Random chance. The cold spot's temperature deviation is so extreme that the probability of it appearing by accident in a universe governed by standard physics is less than 1 in 50. That's not just unlikely, it's a red flag waving in the face of our best theories. Some researchers have tried tweaking the numbers, suggesting maybe the cold spot is just a rare statistical fluke, a cosmic roll of the dice that landed in our line of sight. But when independent observations from multiple telescopes all confirm the same anomaly, coincidence starts to look like a cop-out. This leaves us at a crossroads. With the supervoid theory crumbling and random chance looking increasingly improbable, the cold spot is no longer just a curiosity, it's a crisis, a crack in the foundation of modern cosmology. And when the usual explanations fail, that's when the most thrilling possibilities come into play. If the cold spot isn't a void and isn't a fluke, could it really be something far more extraordinary? A mark left by something beyond our universe, the kind of clue that doesn't just solve a mystery but rewrites the rules entirely. Imagine our universe as one bubble in an ocean of foam, countless others drifting alongside ours, each with its own physics, its own timeline, its own version of existence. This is the multiverse theory in a nutshell, and it's not just wild speculation. Some of the brightest minds in physics argue that if such parallel universes exist, they might occasionally brush against one another, leaving behind cosmic fingerprints. That's where the cold spot comes in. What if this anomaly isn't just a glitch in the data, but a dent in the fabric of our reality, a mark left by a collision with another universe entirely? The idea hinges on something called eternal inflation, a theory suggesting that our universe is just one of many bubble universes constantly popping into existence within an ever-expanding multiverse. Picture a pot of boiling water with bubbles forming, growing, and sometimes merging. Now replace the water with space-time itself and those bubbles with entire universes. If two of them touched even briefly, the energy released could create a disturbance, a kind of cosmic ripple. In our universe, that ripple might manifest as a cold spot in the cosmic microwave background, a relic of that long-ago encounter. It's a staggering thought, but here's where it gets even wilder. These collisions wouldn't play out like two planets smashing together in space, because each bubble universe exists within its own separate space-time. A collision would happen in higher dimensions beyond our perception. Think of it like two soap bubbles floating in air when they merge. The point of contact isn't just on their surfaces, but in the space between them. Translating that to universes, the collision would leave an imprint not in any one place, but across an entire region of space-time. That's exactly what we see in the cold spot, an anomaly that defies local explanations, stretching across nearly 2 billion light-years. Physicists have even run supercomputer simulations to test this idea. When they modeled colliding bubble universes, the results showed distinct signatures, circular patterns of temperature variation in the cosmic microwave background. Remarkably, the cold spot matches those predictions. It's not a perfect fit yet, but the similarities are too striking to ignore. Of course, this isn't proof. It's a tantalizing hint, a whisper from the edges of reality. But if true, it would mean the cold spot isn't just a curiosity. It's a message, a relic of a moment when our universe touched something beyond itself. Not everyone is convinced, and for good reason. Extraordinary claims demand extraordinary evidence, and right now, the cold spot could still be a statistical fluke or an artifact of incomplete data. But here's what's undeniable. If conventional explanations keep falling short, we might need to consider the unthinkable. After all, history has shown us that every time we've assumed we're alone, whether as a planet, a star, or a galaxy, the universe has proved us spectacularly wrong. Why should this time be any different? Let's peel back the layers of the multiverse theory, not as some far-fetched sci-fi trope, but as a legitimate scientific framework that's reshaping how we understand reality. At its core, the multiverse suggests our universe isn't the only one. Instead, it might be just one bubble in an endless cosmic froth, each bubble governed by its own unique laws of physics. Think of it like a pot of water boiling on a stove. As heat makes bubbles rise and pop, the fabric of spacetime itself could be bubbling with universes, each born from quantum fluctuations in an eternally expanding soup of energy. This idea stems from a concept called eternal inflation, a twist on the Big Bang theory. Imagine inflation as a balloon that never stops blowing up. Our universe is one tiny patch where inflation slowed, allowing stars and galaxies to form. But beyond our observable horizon, inflation might still be running wild, spawning new universes endlessly. Each of these bubble universes pinches off with its own physical constants, maybe one where gravity is stronger, another where time runs backward. It's not just hypothetical. The math behind particle physics and cosmic inflation practically demands this possibility. Now, here's where it gets mind-bending. These bubbles don't exist in isolation. Floating in a higher dimensional soup, they might occasionally brush against one another. Picture two soap bubbles drifting in air. When they touch, their surfaces ripple at the point of contact. Translate that to universes, and a collision could leave a mark, a distortion in the cosmic microwave background, like the cold spot we've been studying. The difference: instead of soapy water, the collision happens through dimensions we can't perceive, imprinting a scar across space itself. Critics argue this sounds more like metaphysics than physics, but the numbers tell a different story. When researchers model these collisions using supercomputers, the simulations produce patterns eerily similar to the cold spot's temperature variations. It's not proof yet, but it's a clue written in the language of mathematics. And if we're right, the cold spot isn't just a cosmic oddity. It's a postcard from another reality, suggesting we're part of something infinitely grander than we ever imagined. Quantum mechanics has a way of turning the ordinary into the extraordinary, and when it comes to parallel universes, it doesn't hold back. At the subatomic level, particles exist in a haze of possibilities, a quantum superposition where an electron can spin both clockwise and counterclockwise simultaneously, where a photon can act as both a wave and a particle. It's only when we observe these particles that they choose a state, or so we thought. But what if that choice isn't a choice at all? What if every possible outcome actually happens, branching off into its own separate reality? That's the spine-tingling premise of the many worlds interpretation, one of quantum mechanics' most daring explanations for how parallel universes might emerge from the fabric of reality itself. Picture a single decision like flipping a coin. In our everyday experience, it lands on heads or tails, but according to many worlds, the moment that coin spins, the universe splits. One version of reality sees heads, another tails. Each outcome plays out in its own timeline, its own universe, completely separate yet equally real. And this isn't just happening with coin flips. Every quantum event, every particle interaction, every uncertain measurement triggers an explosion of branching realities. Before long, you're not looking at a handful of parallel worlds, but an infinite tapestry of them, each slight variation spawning new universes where history unfolds in ways we can't even fathom. This isn't science fiction. The math behind quantum mechanics supports this mind-bending idea. When Hugh Everett first proposed many worlds in the 1950s, he wasn't trying to rewrite reality. He was simply following the equations to their logical conclusion. Unlike the traditional Copenhagen interpretation, which insists particles collapse into a single state when observed, Everett's theory treats the universe as a wave function that never stops expanding. There's no collapse, just endless branching. Critics argue it's an extravagant solution, but supporters counter that it's actually the simplest explanation, free of the mysterious observer effect that other interpretations rely on. Now, here's where things connect to our cosmic cold spot. If the multiverse is constantly bubbling with new universes, could some of them have brushed against ours in those earliest moments? Quantum fluctuations, tiny, random changes in energy, are thought to have seeded the universe's first structures, the wrinkles that grew into galaxies. But what if those same fluctuations didn't just shape our universe, but also nudged other bubbles of reality close enough to leave a mark? The cold spot could be evidence of exactly that, a quantum ripple on a cosmic scale. Of course, not every physicist embraces many worlds or its multiverse implications. Some favor alternative interpretations like pilot wave theory or quantum decoherence, which don't require infinite universes. But the beauty of science is in its willingness to chase down every possibility, no matter how strange. After all, history's greatest breakthroughs often started as ideas too outrageous to believe until the evidence tipped the scales. Whether the cold spot is proof of parallel universes or just another cosmic mystery, one thing's certain: quantum mechanics has already shown us that reality is far wilder than we ever imagined. And if there's one lesson to take from all this, it's that the universe loves a good surprise. To understand how a collision between universes could leave behind a cold spot in the cosmic microwave background, we need to step into the bizarre physics of the multiverse. Picture two bubble universes drifting through a higher dimensional space, their edges rippling with the energy of inflation, the same force that drove our universe's explosive expansion after the Big Bang. If these bubbles brushed against each other, even for an instant, the energy exchange at the boundary would send shockwaves rippling through both realities. But here's the twist: because the collision happens outside our familiar three dimensions, the imprint it leaves wouldn't look like a crater or a scar. Instead, it would distort the very fabric of space-time itself, like a pebble dropped into a pond, except the ripples would freeze into the cosmic microwave background as a lingering chill. Here's how it works. When two universes collide, the energy at the boundary isn't just exchanged. It's redistributed in a way that alters the density of matter and radiation in the affected region. Think of it like two hands clapping together in a room full of fog. The force of the collision pushes some of the fog away, leaving a temporary thinning in that spot. Now scale that up to cosmic proportions. The fog is the primordial plasma of the early universe, and the hands are the edges of two bubble universes slamming together. The collision would siphon energy out of our universe's plasma in that area, cooling it slightly compared to its surroundings. Over billions of years, as the universe expanded and that plasma cooled into the microwave background we see today, the dip in temperature would remain, a fossilized echo of that long-ago encounter. But why a cold spot and not a hot one? The answer lies in the way inflation stretches space-time. During a collision, the energy drained from our universe's boundary would effectively steal thermal energy from the cosmic microwave background in that region. It's like opening a freezer door in a warm kitchen. The rush of cold air doesn't add chill to the room so much as it pulls heat away. In cosmic terms, the collision's energy transfer would leave that patch of the CMB with fewer photons and thus a lower temperature. Supercomputer simulations support this, showing that universe collisions tend to produce cold, circular patterns in the CMB uncannily similar to the one we've observed. The real clincher: these collisions wouldn't just leave a random blotch. The physics predicts a very specific signature, a gradient of temperature changes, cooling toward the center and smoothing out at the edges like a bullseye painted in microwaves. That's exactly what astronomers see in the cold spot. It's not just a uniform dip, it's structured, with layers of variation that match what a collision model would produce. Of course, there are other possible explanations, like cosmic textures or rare sound waves in the early universe, but none fit the data as neatly as the collision hypothesis. And if that's true, then this cold spot isn't just a curiosity. It's a message in a bottle from beyond the edge of reality, waiting to be decoded. The key to unlocking the mystery of the cold spot lies not in telescopes, but in supercomputers, massive machines crunching numbers to simulate the birth of the universe itself. Scientists have spent years constructing intricate mathematical models to test whether a collision with another universe could leave behind the exact kind of anomaly we see in the cosmic microwave background. These aren't just simple animations, they're full-scale reconstructions of reality, governed by the laws of quantum physics and general relativity, tracing the evolution of spacetime from its earliest moments to the present day. One groundbreaking simulation, led by researchers at Durham University, recreated what would happen if two bubble universes collided in the multiverse's higher dimensional landscape. The results were astonishing. When these cosmic bubbles brushed against each other, they produced a distinct pattern, a circular imprint where the temperature of the simulated cosmic microwave background dropped sharply at the center, then gradually smoothed out toward the edges. Sound familiar? It's a near-perfect match for the real cold spot structure. Even the size lined up. The simulated collision created a region roughly 2 billion light-years across, eerily close to the actual anomaly scale. But how do you even simulate something as abstract as a universe collision? The secret lies in the mathematics of inflationary cosmology. Researchers start by programming the equations that describe how spacetime expands during inflation, the rapid stretching of the universe that occurred fractions of a second after the Big Bang. Then they introduce a second bubble universe with its own inflationary parameters and let the model calculate what happens when the two collide. The simulations account for everything from how energy transfers at the boundary to how gravitational waves might ripple through the early universe. What's fascinating is that these models don't just produce vague resemblances, they make specific, testable predictions. For instance, if the cold spot were caused by a universe collision, the simulations suggest we should also find subtle distortions in the polarization of the CMB's light around the edges of the anomaly. These twisted patterns would act like cosmic fingerprints, unique to collisions and nearly impossible to mimic through other processes. Teams are now scouring data from the Planck satellite and next-generation observatories, hunting for these telltale signs. Critics argue that simulations, no matter how advanced, can't replace hard evidence, and they're right, these models are tools, not proof. But here's what's remarkable. Every time researchers tweak the simulations to test alternative explanations, cosmic voids, rare density fluctuations, even instrumental errors, nothing reproduces the cold spot's precise characteristics as convincingly as the collision scenario. It's like trying to fit a key into a lock. Most theories don't even turn the mechanism, but the multiverse model, it slides in with a click. Of course, science demands more than just a good fit. That's why the next generation of simulations is pushing further, incorporating data from galaxy surveys and gravitational wave detectors to refine the predictions. If future observations uncover those polarization patterns or correlations with large-scale cosmic structures, the cold spot could transform from a mystery into a milestone, the first tangible evidence that we're not alone in the multiverse. Until then, these digital universes remain our best window into what might be lurking beyond the edge of reality. For all its tantalizing possibilities, the collision theory faces fierce skepticism from a significant portion of the scientific community. One of the loudest critiques comes from proponents of Occam's razor, the principle that, all else being equal, the simplest explanation is usually the right one. To many physicists, invoking an entire parallel universe to explain a single anomaly in the cosmic microwave background feels like using a sledgehammer to crack a walnut. As Dr. Katie Mack, a renowned cosmologist, puts it, extraordinary claims require not just extraordinary evidence, but a complete exhaustion of ordinary explanations first. And right now, many argue we haven't reached that point. Take the cold spot's temperature profile, for example. While simulations show that a universe collision could produce a similar pattern, so could other, less radical phenomena. Cosmic textures, hypothetical wrinkles in spacetime left over from the early universe, could mimic the same temperature dip without requiring a multiverse. Even more mundanely, statistical flukes happen. The universe is vast and improbable events inevitably occur somewhere. As Princeton's David Spergel points out, If you search enough sky, you'll always find something weird. That doesn't mean it's evidence of a new reality. The lack of direct evidence is another sticking point. Unlike gravitational waves or dark matter, which leave multiple traces across different observations, the cold spot stands alone. There's no secondary signal, no corroborating anomaly in galaxy distributions or gravitational lensing that definitively points to a collision. Harvard's Avi Loeb cautions, science thrives on reproducibility. Until we see this pattern elsewhere in the cosmos or detect its unique signatures in other data, it's premature to call it proof of anything beyond our current physics. Then there's the sheer unpredictability of multiverse theories. If bubble universes collide randomly, why haven't we found more cold spots? Shouldn't the cosmic microwave background be littered with these imprints? The absence of additional anomalies makes some researchers question whether we're overinterpreting a single data point. As one skeptical astrophysicist quipped, "You don't rewrite cosmology based on a cosmic typo." Yet perhaps the most measured criticism comes from those who acknowledge the theory's creativity but stress its untestability. Without a way to observe these other universes directly or predict when and where collisions might leave marks, the multiverse hypothesis risks slipping into metaphysics. Nobel laureate George Smoot summed it up: "It's a beautiful idea, but until it makes falsifiable predictions, it's not science, it's speculation wearing a lab coat." That said, even skeptics admit the cold spot remains unexplained. The real debate isn't about dismissing the collision theory outright, but about how much weight to give it while alternatives remain unexplored. After all, science progresses not by jumping to the most exotic explanation, but by systematically ruling out the mundane. Until then, the cold spot lingers a riddle wrapped in a mystery at the edge of our understanding. While the collision theory dazzles with its multiverse implications, there's another class of explanations that don't require parallel realities, just the strange physics of our own universe in its infancy. Enter topological defects, bizarre wrinkles in space-time, cosmic scars left behind when the fabric of reality underwent dramatic phase transitions moments after the Big Bang. Think of the early universe like molten metal cooling into a solid. As it crystallized into the stable cosmos we know today, imperfections might have frozen into its structure, cosmic cracks where the rules of physics twist slightly out of alignment. Among these exotic possibilities, one stands out: cosmic textures. Unlike voids or collisions, textures aren't objects in space. They're kinks in spacetime itself, regions where the underlying fields that govern reality got tangled during the universe's rapid expansion. Picture a knitted sweater snagging on a branch. The yarn doesn't disappear, it just twists into a new configuration. In cosmic terms, that snag could create a localized disturbance in the gravitational field, subtly warping the path of light and altering temperatures in the cosmic microwave background. How would this explain the cold spot? When light from the CMB passes near a cosmic texture, it experiences what physicists call the Sachs-Wolf effect, a shift in energy caused by climbing in and out of gravitational hills. A texture's unique topology would distort this journey, leaving a distinct cold imprint in the radiation we observe today. Computer simulations show these defects could produce signatures remarkably similar to the cold spot's bullseye pattern, complete with concentric rings of temperature variation. But textures aren't the only topological oddities in play. Other defects like cosmic strings or domain walls might also leave imprints on the CMB. Cosmic strings, hypothetical one-dimensional filaments thinner than an atom but stretching across the universe, could have sliced through space in the early cosmos, creating shockwaves that cooled surrounding plasma. Domain walls, two-dimensional sheets separating regions of space with different quantum properties, might have acted like cosmic mirrors, redirecting photons in ways that left temperature anomalies. The challenge: unlike colliding universes, these defects should be everywhere. If textures or strings were common in the early universe, we'd expect to find dozens of cold spots scattered across the sky, not just one solitary anomaly. Some researchers argue we might be seeing the lone survivor of an otherwise vanished population, a cosmic fossil preserved by chance. Others suggest the cold spot could be a particularly massive defect, its rarity explained by the same improbability that lets some snowflakes grow far larger than others in a storm. What makes these theories compelling is their grounding in well-studied physics. Phase transitions and symmetry breaking the processes that could create topological defects are observed everywhere from magnet formation to superfluid helium. The universe itself may have undergone similar transitions as it cooled, meaning defects wouldn't require new physics to exist, just an amplification of phenomena we already understand. Yet, like all explanations for the cold spot, the defect theory has gaps. No one has directly detected a cosmic texture or string, and their predicted gravitational lensing effects haven't shown up in surveys. The search continues with increasingly sensitive instruments, hunting for the telltale warping of starlight or sudden jumps in cosmic radio waves that could betray these spacetime wrinkles. Whether the cold spot stems from defects, collisions, or something else entirely, its mystery exposes how much we still don't understand about the universe's first moments. Every anomalous photon in that chilly patch of sky carries a message from a time when reality itself was taking shape, and decoding it might require rewriting physics as we know it. Before we rewrite the laws of physics to accommodate parallel universes, there's a far simpler question we need to confront. What if the cold spot isn't cosmic at all? What if it's just a glitch in the data, a trick of the instruments rather than the universe? Given how much hinges on this anomaly, scientists have spent years scrutinizing every possible mundane explanation, from telescope calibration errors to interference from our own cosmic backyard. Take foreground contamination, for example. The cosmic microwave background isn't the only microwave light reaching our telescopes. Dust in our galaxy, radiation from distant quasars, even the faint glow of electrons zipping through galaxy clusters, all of these can muddy the signal. It's like trying to listen to a whisper in a crowded room. Could something in that noise be masquerading as a cold spot? Researchers have meticulously mapped these foreground sources, using multiple wavelengths to subtract their contributions. Yet after all that filtering, the cold spot stubbornly remains. Then there's the specter of instrumental error. Mapping the CMB isn't like snapping a photo with your phone. Telescopes like WMAP and Planck scanned the sky for years, stitching together millions of measurements. A slight miscalibration in a detector or a hiccup in data processing could theoretically create artificial patterns. But here's the catch. The cold spot appears in data from both missions, despite their completely independent instruments and analysis pipelines. The odds of two separate telescopes making the same bizarre mistake. Astronomers put it at less than 1 in 1,000. Some skeptics point to more subtle artifacts, like the way raw data is processed into a final map. The CMB isn't observed directly. It's reconstructed using complex algorithms that account for everything from telescope beam shapes to galactic rotation. Could a flaw in that reconstruction introduce a phantom cold spot? Teams have tested this by tweaking their processing methods, even throwing out suspect data points. The anomaly persists. Perhaps the most convincing argument against the glitch theory comes from cross-checking with other observations. If the cold spot were an artifact, it wouldn't correlate with anything in the real universe. But recent studies have found faint hints of corresponding large-scale structures, subtle voids, and galaxy distributions that align with the cold spot's location. It's not proof of a parallel universe, but it's strong evidence that we're seeing something real, not just a quirk of the data. That doesn't mean the case is closed. New telescopes like the Simons Observatory and next-generation space missions will examine the cold spot with unprecedented precision. They'll hunt for the telltale polarization patterns predicted by collision models and rule out lingering doubts about foregrounds or processing. Until then, the glitch hypothesis remains on life support, not quite dead, but fading fast against the weight of evidence, because sometimes the most extraordinary answer isn't just possible, it's the only one left standing. Right now, the fate of the cold spot, and perhaps the multiverse itself, rests in the hands of a new generation of telescopes, instruments so advanced they'll peer deeper into the cosmic microwave background than ever before. Leading the charge is the Simons Observatory, a suite of ultra-sensitive telescopes perched high in Chile's Atacama Desert, where the thin, dry air offers a crystal-clear window to the cosmos. Unlike its predecessors, this facility won't just map the CMB's temperature, it'll capture its polarization, the faint directionality of those ancient microwaves, with precision down to a fraction of a degree. Why does that matter? If the cold spot was forged by a collision with another universe, the polarization patterns around its edges should twist in a very specific way, like swirls left in sand by a receding tide. The Simons array, already collecting data, could spot those telltale twists within the next few years. But the real game changer lies even further ahead. The proposed Lightbird satellite, a space-based observatory with a single burning mission, to hunt for primordial gravitational waves and anomalies in the CMB with unprecedented clarity. Imagine comparing a foggy photograph to a high-definition scan. Lightbird detectors, shielded from Earth's atmospheric noise, will scan the entire sky in multiple frequencies, filtering out foreground interference to reveal the cold spot's true structure. If there's hidden detail in that anomaly, layers of temperature variation or polarization signals that current telescopes can't resolve, Lightbird will expose them. The satellite's resolution is so sharp it could distinguish between a cosmic texture's subtle warp and the bullseye signature of a universe collision. Then there's CMB-S4, a ground-based project so ambitious it'll deploy 500,000 detectors across 2 continents, creating the most detailed CMB map in history. This isn't just an upgrade, it's a revolution. Where Planck mapped the sky with hundreds of pixels, CMB-S4 will use millions, capturing variations 100 times fainter than what we've seen before. It's like switching from a blurry weather radar to a live satellite feed during a storm. With that level of detail, researchers could finally answer the cold spot's biggest question: is it alone? If other, fainter anomalies lurk in the CMB, hidden by noise in earlier surveys, they'll emerge in CMB-S4's data, revealing whether we're looking at a rare fluke or a pattern that points to deeper physics. But the most tantalizing possibility lies in combining these observations with entirely new ways to probe the cosmos. The next generation of gravitational wave detectors, like the space-based LISA mission, could uncover ripples in spacetime that trace back to the universe's earliest moments, ripples that might carry echoes of a collision. Meanwhile, galaxy surveys like the Dark Energy Spectroscopic Instrument are mapping millions of galaxies in 3D, hunting for large-scale structures that align with the cold spot's location. If a cosmic texture or void left that imprint, its gravitational shadow should distort the distribution of galaxies in a predictable way. What's thrilling is that we're not just waiting decades for answers. The Simons Observatory's first results could land within the year, with Lightbird and CMB-S4 following in the mid-2000s. For the first time, we're not just speculating about the cold spot, we're building the tools to dissect it, to interrogate it, to force it to reveal whether it's a cosmic mirage or a crack in reality itself. And no matter what these telescopes find, the outcome reshapes our understanding of the universe. Either the anomaly fades under scrutiny, reminding us that even the strangest quirks of nature often have mundane explanations, or it stands firm, defiant, forcing us to confront the breathtaking possibility that our universe is just one thread in an infinite cosmic tapestry. What if we woke up tomorrow to headlines confirming the cold spot was indeed a scar from a collision with another universe? Beyond rewriting physics textbooks, such a discovery would send shockwaves through our very understanding of existence. For centuries, humanity has grappled with its place in the cosmos, first realizing Earth wasn't the center of the solar system, then learning our galaxy was one among billions. But a multiverse that elevates cosmic humility to an entirely new level. Suddenly, we're not just specks in a vast universe, we're temporary residents in one bubble among countless others, each with its own version of history, its own laws of physics, perhaps even its own civilizations asking the same questions. This revelation would force us to confront existential puzzles we've only toyed with in philosophy classes. If other universes have different physical constants, say, a stronger gravitational force or a slower speed of light, does that mean life as we know it couldn't exist there? Or might entirely unfamiliar forms of life thrive under those alien rules? The anthropic principle, which suggests our universe's laws seem fine-tuned for life, takes on a haunting new dimension. Instead of wondering why our cosmos is so perfectly calibrated for stars, planets, and biology, we'd face the staggering possibility that every conceivable configuration exists somewhere in the multiverse. We don't inhabit a special universe, we inhabit one of the rare ones where beings like us can even ponder the question. Then there's the elephant in the room. If parallel universes exist, could they contain parallel versions of us? The idea isn't just science fiction, it's a legitimate branch of quantum mechanics called the many worlds interpretation. Every decision, every random quantum event might spawn new timelines in neighboring universes. Think of it like a cosmic tree with branches splitting infinitely. Somewhere out there, a version of you chose a different career, a different partner, or perhaps never existed at all. It's a dizzying thought, but here's the twist. Even if these alternate selves are real, we'd likely never meet them. The physics that allows bubble universes to collide doesn't necessarily permit travel between them. We might be forever isolated in our own pocket of reality, left to wonder about the roads not taken. This brings us to the limits of science itself. A confirmed multiverse would simultaneously expand our horizons and remind us how much lies beyond our grasp. If other universes operate with different laws, could we ever truly study them? Or would they remain forever hypothetical, like shadows on the wall of Plato's cave? Some theorists argue this pushes cosmology into metaphysics, that if we can't observe or interact with these parallel realities, they might as well not exist. Others counter that the cold spot itself, if proven to be a collision mark, is precisely the kind of observable evidence that keeps the multiverse in the realm of science. Perhaps the most profound shift would be cultural. Throughout history, every expansion of our cosmic perspective has reshaped art, religion, and philosophy. Copernicus demoted Earth from the center of creation. Hubble revealed an expanding universe, banishing the notion of a static, eternal cosmos. A multiverse might do something even more radical, challenge the very idea of uniqueness. If every possible outcome plays out somewhere, does our lives' meaning dilute across infinite realities? Or does it become more precious, knowing this particular iteration of existence is ours alone to experience? Scientists like Sean Carroll argue that a multiverse doesn't diminish our significance, it reframes it. We're not insignificant because we're small, we're remarkable because we're here at all, in this specific universe where the conditions align just right to let us ask these questions. The cold spot, if it is indeed a cosmic handshake from another reality, wouldn't just solve a scientific mystery. It would invite us to see ourselves anew, not as the culmination of creation, but as curious witnesses to a reality far grander and stranger than we ever dared imagine. And that's the heart of it. Whether the multiverse is real or not, the mere possibility stretches our minds in ways that redefine what it means to explore. After all, science isn't just about answering questions, it's about discovering which questions are worth asking in the first place. Long before scientists published papers about the cold spot, storytellers were already dreaming of parallel worlds colliding, proof that reality can sometimes be as wild as fiction. Take Marvel's Doctor Strange in the Multiverse of Madness, where the fabric of reality ripples with incursions, catastrophic collisions between universes. The visual effects team didn't just pull those kaleidoscopic distortions from thin air. They tapped into real cosmological theories, echoing the kind of space-time wrinkles physicists predict would form during a universe collision. Hollywood's version is louder, of course, complete with exploding stars and shattering dimensions, but the core idea isn't so different from those sober supercomputer simulations. Then there's Rick and Morty, which treats the multiverse like a cosmic playground, tossing its characters through infinite realities where pizza rules the world or humans never evolved. While the show's interdimensional hijinks are pure absurdity, they nail a fundamental truth. If parallel universes exist, their diversity would dwarf anything we could imagine. Scientists might speculate about bubble universes with altered physical constants, but Rick and Morty runs with it, asking what happens when you meet a version of yourself who's a pickle, or worse, a version who actually finished grad school. But pop culture's love affair with the multiverse predates even these modern hits. Classic Star Trek episodes explored parallel timelines, sliding doors turned quantum, branching into a romantic dramedy, and the Twilight Zone twisted reality with eerie alternate dimensions. What's fascinating is how often these stories stumble onto real science by accident. The One, a 2001 action flick starring Jet Li, hinges on energy redistribution between parallel selves, a premise that bizarrely mirrors theories about quantum entanglement across branching universes. Of course, creative liberties abound. While physicists debate statistical anomalies in microwave data, Everything Everywhere All at Once serves up a multiverse where rocks have feelings and hot dog fingers are a viable evolutionary path. The contrast is delightful. Where science demands painstaking proof, sci-fi thrives on unshackled imagination, yet both share a common goal: to stretch our understanding of what's possible. The real magic happens when fiction circles back to inspire science. Carl Sagan famously credited Star Trek's communicators for seeding the idea of flip phones. Could today's multiverse stories be doing the same? Some researchers admit that pop culture's playful takes help them think outside the cosmological box. After all, if a TV show can imagine a universe where gravity pushes instead of pulls, why couldn't that exist in the quantum foam? Perhaps that's the cold spot's greatest gift. It bridges the gap between equations and daydreams. Whether it's a Marvel blockbuster or a niche physics paper, we're all chasing the same thrill: the dizzying thought that reality might be bigger, weirder, and more interconnected than we ever dared believe. And in that sense, every wild multiverse story, no matter how outlandish, is a tribute to human curiosity's endless reach. Let's be real, when you hear cosmic cold spot, your brain probably jumps straight to sci-fi tropes, interdimensional portals, alien messages, or some galactic-sized freezer malfunction. The internet certainly hasn't helped, with headlines screaming things like "NASA finds gateway to another dimension." Here's the thing: actual scientists aren't running around shouting about stargates. The reality is far stranger and more grounded than the hype would have you believe. Take the portal myth. No, the cold spot isn't some shimmering doorway where you'll meet your alternate universe self, unless your doppelganger enjoys floating in a near-perfect vacuum at -270 degrees Celsius. What researchers are suggesting is subtler. If another universe brushed against ours, it might have left a gravitational dent, like a couch cushion holding the shape of someone who just stood up. The difference: this dent is a billion light-years wide and requires quantum physics to explain. Less Doctor Strange, more extremely advanced geometry homework. Then there's the idea that the cold spot breaks physics. Sensational stuff, but misleading. Science isn't a house of cards where one anomaly collapses everything. It's more like a puzzle. When a piece doesn't fit, you don't burn the puzzle, you check if you've misread the picture on the box. In this case, the cold spot isn't breaking our models, it's nudging us to refine them. Maybe that means new physics, maybe it's a statistical fluke, but either way, physicists aren't panicking. They're excited, and let's debunk the biggest whopper of all, that this proves parallel universes exist. Headlines love that leap, but scientists, they're way more cautious. Right now, the cold spot is a hint, not a smoking gun. It's like finding a single, giant footprint in the woods. Could it be Bigfoot? Sure. Could it also be a guy in oversized boots? Absolutely. Until more evidence rolls in, the multiverse remains a thrilling maybe, not a done deal. What's hilarious is how these myths snowball. One researcher muses, hey, maybe this could relate to bubble universes, and suddenly tabloids declare, scientists confirm ghost universe haunting our sky. Meanwhile, the actual paper is buried in equations about microwave photon densities. The lesson: if a cosmic headline sounds like a movie tagline, grab some popcorn, but also grab the original study. Because the truth isn't always less cool than fiction. Sometimes it's just cooler in ways you'd never expect, like realizing that a faint, ancient chill in the sky might be the closest we'll ever get to high-fiving another reality. Laura Mersini-Houghton, the theoretical physicist who famously proposed the multiverse collision theory, doesn't mince words when it comes to the cold spot. This isn't just data, it's a message, she insists. When you run the numbers, the probability of this anomaly appearing by chance is like winning the cosmic lottery 10 times in a row. It's too precise, too structured to dismiss as noise. Her groundbreaking simulations showed that when bubble universes collide in higher dimensional space, they leave behind circular imprints in the cosmic microwave background uncannily similar to what we're seeing. The cold spot isn't a flaw in our models, she argues. It's a flaw in our imagination. We've been thinking too small, but not everyone is convinced. Renowned cosmologist George Efstathiou, who led the Planck satellite's analysis of the CMB, remains skeptical. Extraordinary claims require extraordinary evidence, and right now we just don't have it, he counters. The cold spot is intriguing, sure, but so were other anomalies that turned out to be instrumental artifacts or statistical quirks. Until we rule out every mundane explanation, invoking parallel universes is premature at best. Efstathiou's team has spent years testing alternative scenarios, from subtle foreground interference to rare gravitational lensing effects. Science moves slowly for a reason, he adds. If we start rewriting textbooks every time we see something odd, we'll end up with more fiction than physics. The debate gets even livelier when you bring in Andre Linde, one of the architects of inflationary cosmology. He sees the cold spot as a thrilling clue, but not necessarily proof of collision. Could it be a multiverse signature? Absolutely, Linde muses. But it could also be a cosmic defect, a frozen ripple from the universe's birth pangs. The beauty is in the mystery. His work on eternal inflation lays the groundwork for Mersini-Houghton's theories, yet he cautions against overinterpretation. The multiverse isn't some get-out-of-jail-free card for unexplained data. If we're going to take it seriously, we need predictions, not just postcards from hypothetical realities. Then there's the pragmatic voice of cosmologist Joanna Dunkley, who emphasizes the human element behind the data. We're talking about minute temperature differences in microwaves that have traveled 14 billion years to reach us, she points out. The margin for error is razor thin. Maybe the cold spot is real, maybe it's noise, but either way, it's a reminder of how much we still don't know. Dunkley's team has focused on refining CMB measurements, stripping away biases and systematic errors. The universe doesn't owe us easy answers, she laughs. If it did, we'd all be out of jobs. What's striking is how these researchers, despite their disagreements, share a sense of exhilaration. The cold spot isn't just a puzzle, it's a catalyst pushing cosmology to its limits. Mersini-Houghton puts it best: science thrives at the edge of the unknown. Whether this anomaly leads us to a multiverse or just a deeper understanding of our own universe, one thing's certain: we're standing at the threshold of something extraordinary. And in the end, that's what makes this debate so thrilling. It's not just about who's right or wrong, it's about how far we're willing to let the evidence take us. While parallel universes and cosmic defects steal the spotlight, there's a whole menu of bizarre possibilities that could explain the cold spot, each more mind-bending than the last. Let's start with primordial black holes, hypothetical relics from the universe's first chaotic seconds. Unlike the black holes we know born from collapsing stars, these ancient behemoths could have formed when dense pockets of the infant cosmos collapsed under their own gravity. Picture a black hole the size of a marble but with the mass of a planet lurking in the cold spot's darkness. Its gravitational pull might warp space-time so severely that light passing through gets stretched, cooling the CMB in that region like a cosmic freezer. But here's the twist: primordial black holes wouldn't just sit there quietly. They'd annihilate matter around them, spewing radiation that should leave other detectable imprints. So far, telescopes haven't found that smoking gun. Still, some theorists argue we might be looking at a particularly sneaky specimen, one that's either unusually massive or nestled in just the right spot to hide its telltale emissions. Then there's the radical idea that the cold spot isn't pointing to hidden objects, but to hidden flaws in our understanding of gravity itself. Einstein's theory of general relativity has been the gold standard for a century, but what if it breaks down on cosmic scales? Modified Newtonian dynamics, or MUND, suggests gravity behaves differently in areas of extremely low density, like the vast emptiness between galaxy clusters. If true, the cold spot could be a gravitational illusion, a place where light bends in unexpected ways because the rules themselves are bending. Critics dismiss MUND as a fringe idea, but it's gained traction because it explains certain galactic motions without invoking dark matter. Could it also solve the cold spot puzzle? Simulations show that tweaking gravity's laws might produce CMB anomalies resembling what we observe. Yet without experimental proof, it remains a tantalizing what-if the kind of idea that keeps physicists awake at night, scribbling equations on napkins. For those craving even wilder possibilities, consider cosmic strings, not the microscopic kind from string theory, but gargantuan defects thinner than an atom but stretching across the universe. These theoretical scars from the Big Bang would carry unimaginable tension, warping space-time around them like a taut wire bending a bedsheet. If one sliced through the cold spot region, it could create gravitational lensing effects that mimic a temperature drop. The catch: cosmic strings should also produce double images of distant galaxies and bursts of gravitational waves, neither of which we've spotted in the cold spot's neighborhood. And then there's the meta-explanation that the cold spot isn't an anomaly at all, but evidence we're misreading the cosmic microwave background entirely. Some researchers propose that the CMB's uniformity might be an artifact of how we model the universe's expansion, a kind of cosmic mirage. If we're living in a region of space with slightly different expansion rates, our measurements could be skewed, making certain areas appear colder than they really are. It's like thinking you found a dent in your car hood, only to realize it's just a trick of the light. The beauty of these alternatives isn't just their creativity, it's how they reveal science as a living process. Every unexplained anomaly is an invitation to question, to test, to imagine. Whether the cold spot stems from black holes, broken gravity, or something entirely uncharted, one thing's clear: the universe still holds cards we haven't even dreamed of yet. And that's what makes this mystery so electrifying, not because it might be solved tomorrow, but because it might not be, because the answer could rewrite reality itself. History has a way of humbling even the most confident scientists, and nothing proves that quite like cosmic anomalies. Take the infamous Pioneer anomaly, a puzzle that stumped astrophysicists for decades. When NASA Pioneer 10 and 11 spacecraft drifted toward the edge of the solar system in the 1980s, something bizarre happened. They began slowing down as if an invisible force were tugging them backward. The deceleration was tiny, just a fraction of a nanometer per second squared, but it defied every calculation. Some speculated about unknown planets, others whispered of new physics. Sound familiar? It wasn't until 2012 that researchers cracked the case. The spacecraft's own heat radiation, bouncing off their asymmetrical bodies, was pushing them ever so slightly off course. A mundane explanation for what once seemed like a violation of the laws of motion. Or consider the faster-than-light neutrino debacle of 2011. Scientists at CERN announced they detected subatomic particles called neutrinos traveling just a hair faster than light, an impossibility under Einstein's theory of relativity. The media erupted with talk of shattered physics and rewritten textbooks, but the truth was far simpler. A loose fiber optic cable in the timing system had introduced a minuscule error. Once fixed, the neutrinos fell obediently back into Einstein's framework. These episodes aren't just footnotes, they're masterclasses in how science works. Every groundbreaking discovery starts as an anomaly, a stubborn data point that refuses to fit. The key is patience. When Uranus's orbit wobbled strangely in the 19th century, astronomers didn't invent new physics, they predicted Neptune's existence before spotting it. When Mercury's orbit didn't quite match Newton's predictions, Einstein didn't dismiss the discrepancy, it became evidence for general relativity. The cold spot fits squarely in this tradition. Like the Pioneer anomaly, it could be an observational quirk. Like the neutrino scare, it might vanish under sharper scrutiny. Or, like Uranus's wobble, it could point to something revolutionary, a cosmic Neptune waiting beyond the edge of our understanding. That's the thrill of anomalies. They force us to question, to refine, sometimes to tear up the map entirely. Whether the cold spot ends up as a cautionary tale or a paradigm shift, one thing's certain: it's already done its job by reminding us how much we still have left to explore. The cold spot isn't just a curiosity, it's a crack in the foundation of modern cosmology, forcing scientists to rethink what they thought they knew about the universe's architecture. For decades, the standard model of cosmology has been remarkably successful, a framework so sturdy it's often called the concordance model. It describes a universe born from the Big Bang, filled with dark matter, driven apart by dark energy, and governed by Einstein's theory of gravity. But the cold spot, it's like finding a single puzzle piece that refuses to fit, no matter how you twist it. The anomaly's sheer size and temperature deviation defy the model's predictions, exposing gaps in our understanding of how the universe evolved. This isn't just academic nitpicking. The cold spot has become a rallying point for cosmologists who argue that our current theories might be incomplete. Take inflation, the idea that the universe expanded exponentially in its first moments. Inflation explains the CMB's overall smoothness, but the cold spot's peculiar structure suggests something might have happened during or even after inflation that our models don't account for. Some theorists propose multi-field inflation, where additional quantum fields interacted in ways that left behind anomalies like the cold spot. Others wonder if dark energy, the mysterious force accelerating the universe's expansion, could behave differently in certain regions, warping space-time in ways we haven't yet imagined. The cold spot has also reignited debates about the universe's geometry. For years, we've assumed space is flat, meaning parallel lines stay parallel forever. But what if it's subtly curved, like the surface of a giant, invisible sphere? A curved universe could distort the CMB in unexpected ways, potentially creating localized cold areas. While current measurements still favor flatness, the cold spot keeps the door open for alternative geometries, reminding us that even foundational assumptions deserve scrutiny. Perhaps most fascinating is how the anomaly has breathed new life into once fringe ideas. Before the cold spot, theories like the multiverse or exotic topological defects were largely speculative, interesting thought experiments with little observational backing. Now they're serious contenders, debated in peer-reviewed journals and tested with supercomputer simulations. The cold spot hasn't proven these ideas correct, but it's given them something rare in science, a testable hook. If future telescopes find specific polarization patterns or gravitational lensing effects around the anomaly, it could validate one of these radical theories, rewriting cosmology overnight. Yet amid all this upheaval, the cold spot has also taught scientists humility. It's a reminder that the universe doesn't owe us tidy answers. Every time we think we've got it figured out, the cosmos tosses us a curveball. Whether the cold spot ends up as a statistical fluke, a sign of new physics, or evidence of a parallel universe, its legacy is already secure. It's pushed cosmology to ask bigger questions, to venture beyond the safe confines of established theory. And that's how science moves forward, not by confirming what we already know, but by stumbling onto the things we don't. What if the cold spot never gives up its secrets? Science is filled with mysteries that refuse to yield, no matter how hard we probe. Some puzzles, like the nature of dark matter or the fate of the universe, linger for decades, even centuries, teasing us with partial clues but never a full reveal. The cold spot could join that elite club of cosmic enigmas, an anomaly that withstands every telescope, every simulation, every brilliant idea we throw at it. And strangely, that might not be a bad thing. Think about the Vikings' WOW signal, a burst of radio waves detected in 1977 that lasted just 72 seconds and was never heard again. Despite decades of searching, we still don't know whether it was an interstellar message, a natural phenomenon, or some bizarre glitch. Yet its mystery has driven generations of astronomers to refine their tools, to listen harder, to question assumptions. The cold spot could do the same. Unsolved puzzles aren't failures, they're guideposts, pointing us toward the gaps in our knowledge where the next breakthroughs might lie. Then there's the beauty of the unknown itself. A universe where every mystery is solved would be a static place with no room for wonder. The cold spot, if it remains unexplained, would be a humbling reminder that reality is stranger and more complex than our models can capture. That's not a weakness of science, it's the very essence of it. The moment we think we've figured everything out is the moment we stop looking. But here's the twist: sometimes the answers come from the most unexpected places. The Michelson-Morley experiment in the late 1800s failed to detect the ether wind scientists thought permeated space. That failure paved the way for Einstein's relativity, rewriting physics entirely. The cold spot might follow a similar path. Even if we never confirm a collision with another universe, the search for an answer could unveil new physics, new ways of seeing the cosmos we hadn't considered before. And that's the real lesson. Science isn't just about solving puzzles, it's about learning how to ask better questions. The cold spot, whether it's a multiverse's calling card or a quirk of statistics, has already expanded our imagination. It's forced us to consider possibilities that once seemed like fantasy, to build tools sharper than we thought possible, and to remember that the universe owes us nothing. The greatest discoveries often begin with a single, stubborn anomaly that refuses to make sense. So if the cold spot stays mysterious, let it. Some secrets are worth the wait. Want to join the hunt for cosmic anomalies from your living room? You don't need $1 million telescope or a PhD in astrophysics, just an internet connection and a curiosity for the unknown. NASA and the European Space Agency have made vast troves of cosmic microwave background data freely available online, including the very maps that first revealed the cold spot. Head over to the Legacy Archive for Microwave Background Data Analysis, or LAMDA, hosted by NASA Goddard Space Flight Center. This digital treasure chest holds raw and processed CMB data from missions like WMAP and Planck, ready for anyone to download and explore. Picture yourself scrolling through those same temperature maps that left scientists scratching their heads, hunting for subtle variations that might hint at something extraordinary. For those who prefer a more guided experience, citizen science platforms like Zooniverse offer hands-on projects where volunteers help classify cosmic data. One standout initiative is Planet Hunters TESS, where amateur astronomers sift through telescope data to spot anomalies, skills that translate perfectly to CMB analysis. Imagine spotting a never-before-seen temperature fluctuation that could be the next big mystery. It's happened before amateurs have identified unusual galaxy formations and even potential exoplanets that algorithms missed. The cold spot could have cousins hiding in plain sight, waiting for a sharp-eyed observer to flag them. If you're feeling ambitious, tools like CMB Fast or Heal Pix let you model cosmic microwave background patterns based on different theoretical scenarios. What happens to the data if you tweak inflation parameters or simulate a universe collision? These programs, once reserved for academics, now sit just a download away for anyone eager to experiment. Online forums like CosmoQuest provide bustling communities where hobbyists and experts trade tips, debate findings, and sometimes collaborate on publishable research. And here's the best part: you don't need to tackle this alone. Local astronomy clubs and university outreach programs often host workshops on interpreting CMB data. Many even partner with schools or libraries to loan out equipment like radio telescopes capable of detecting microwave background signals. Picture a backyard setup where you're not just stargazing but mapping the afterglow of creation itself. The cold spot reminds us that the universe still holds puzzles waiting to be solved, not just by professionals in lab coats but by anyone willing to look closely. Whether you're poring over public datasets or joining a global citizen science project, you're part of a tradition as old as astronomy itself, ordinary people making extraordinary discoveries. Who knows, the next big cosmic revelation might come from your laptop, one curious click at a time. So where does this leave us, staring at a patch of sky that refuses to play by the rules, where the temperature dips just a little too much, where every explanation dangles between tantalizing possibility and frustrating uncertainty? The cold spot is more than a scientific puzzle, it's a mirror reflecting how we grapple with the unknown. On one side, there's the multiverse theory, a cosmic handshake from another reality. On the other, cosmic defects, primordial black holes, even flaws in our own understanding of gravity. Each explanation feels like a thread tugging at a different corner of the tapestry, and we're not yet sure which one will unravel the truth. Think about what's at stake here. If the cold spot is a collision scar, it rewrites our place in existence, proof we're not alone in the grandest sense imaginable. If it's a cosmic texture or void, it reveals hidden physics from the universe's fiery birth. And if it's just a statistical fluke, that's fascinating too, because it means even randomness can carve anomalies so profound they stump us for decades. The beauty isn't in the answer, it's in the hunt. Every telescope pointed at that chilly patch of sky, every supercomputer simulation tweaked and rerun, they're all part of something bigger, humanity's relentless drive to make sense of the cosmos. This is why science thrives on mysteries like the cold spot. They're not roadblocks, they're invitations. A century ago, astronomers debated whether the universe extended beyond the Milky Way. 50 years ago, black holes were theoretical oddities. Today, we're peering at the edge of reality itself, asking if our universe is one bubble in an infinite froth. The cold spot could be the first clue to answering that question, or it might vanish under sharper scrutiny, leaving us with new questions to chase. Either way, the journey is the point. So here's my challenge to you: stay curious. The next breakthrough might not come from a lab or a telescope, but from someone watching this video, scribbling ideas in the margins of their notebook. Maybe you've got a theory about the cold spot, some wild, brilliant hunch no one's considered yet. Drop it in the comments. Science doesn't move forward because a handful of experts have all the answers. It moves because millions of us keep looking up, wondering, and daring to ask, what if? The cold spot reminds us the universe is still full of surprises, and the best discoveries often start with a single, stubborn anomaly that refuses to make sense. And who knows, the next time you gaze at the night sky, remember, out there, hidden in the afterglow of creation, might be a message from another universe. Or maybe just a cosmic prank, laughing at our attempts to figure it all out. Either way, isn't that exhilarating? If the cold spot has left you questioning everything you thought you knew about reality, just wait, we're only scratching the surface. The quantum multiverse, hidden dimensions, and even stranger cosmic anomalies are lurking just around the corner, waiting to bend your mind even further. Want to dive deeper? Hit that like button and subscribe. It's the best way to make sure you don't miss what's coming next. And if you're craving more right now, check out the links in the description for mind-blowing papers, documentaries, and interactive tools to explore these ideas yourself. Who knows, maybe you'll spot the next cosmic anomaly before the scientists do. Until then, keep looking up because the universe is stranger than we can imagine, and the next big discovery might be just one video away. Stay curious.